Number one, so these dots to the right represent positions of two skydivers recorded each second. One of them's in free fall, and the other is parachute open. So this skydiver, you see, is here. After a second, the skydiver is here, and she's here. I think it says she in here, so yeah. She's here, she's here, she's here. She's moving the same distance every second. And since she's traveling the same distance every second, her velocity is the same. Velocity is the distance that you travel within a second. So this is a constant velocity. This skydiver is going from here to here, short distance, from there to there, longer distance. The next second goes an even longer distance. The next second goes an even longer distance. So this skydiver is going fastest within this second, from this position to that position. They're getting faster and faster and faster. So which one's in free fall? This one. Free fall means there's no air slowing you down. You just accelerate forever at negative 10 meters per second squared. So negative 10 meters per second squared is the acceleration here. You can't tell that from the picture, but you can tell that this is the one that's accelerating and this is the one that's not. One thing that I have to be a little careful about is if I write negative 10 meters per second squared, I don't really need the arrow. If I have the arrow, it might even be better to not put the negative there, because this looks like 10 meters per second downward, that's okay. Negative 10 meters per second downward, that's kind of weird. That's a double negative. That might sound like it's going upward. At any rate, Skydiver 2 is in free fall. How can you tell? Because the skydiver moves greater distances with each passing second. Which skydiver is at a constant velocity? Number one, because the skydiver moves the same distance with each passing second. Number two, you're supposed to make a graph showing the velocity and acceleration of someone in free fall or something in free fall. And I chose to do it this way. There are several possibilities over here. There's only one over there. When something is in free fall, it could be a rock thrown off a cliff. It could be, if there's somebody standing here, they drop this rock down off the cliff. Or if you throw something up in the air, it really doesn't matter. If something is in the air, it's going to accelerate downward at negative 10 meters per second squared. If you throw something up, it's actually accelerating that way, which means it's going to go up slower and slower and slower. When it starts to come down, it's still accelerating that way, which means it's going to go faster and faster. Its speed decreases, then its speed increases. But velocity, which means direction, velocity is positive, getting less and less and less positive. Now velocity is zero, now velocity gets negative, getting more and more and more negative. So the upshot of this is, every second that you spend in the air, you're going to lose 10 meters per second. So I started off with something being dropped, having no velocity. After a second, it's going to have 10 less than that meters per second, so it's negative 10. After another second, negative 20. After another second, negative 30. And then after a fourth second, negative 40. Now, it could be that you throw something upward. If something starts with a 50 meter per second velocity, that means it's going up that fast. You could kind of say it's in free fall. It's not falling, but the only thing affecting it is gravity. So my graph would look like this. 50 meters per second. After a second, gravity's going to slow it down to 40, then 30, then 20, then 10. So my graph would look like this. With the acceleration, there's only one thing that you can do here. Negative 10. That is the acceleration of gravity the whole time. And if you're in free fall, that's the acceleration that's affecting you. A quick note to people retaking this test, I'm not going to have exactly the same questions on the test. Some of these might be on there again, or something very similar to them, or it might be something different that's either on the practice test or was in the notes. So don't count on all these questions looking the same. But if you understand them, they'll help you understand the ones in the retake. Number 3, a ball is thrown vertically. This isn't exactly vertical, but it's supposed to show a ball going up, coming down. Does the velocity change? Yeah. Let me jump to this one. Does the acceleration change? No. So like I was saying just a second ago, when it's going up, the acceleration is down. When it's at the top, the acceleration is down. When it's coming down, the acceleration is down. The acceleration doesn't change the whole time. The velocity changes a lot. Here it's going against gravity, so its speed slows down. Here it's going with gravity, so its speed speeds up. I'm talking speed there. Now if I'm talking about velocity, it's got a positive velocity, but it gets lower and lower and lower, and now it starts to have a negative velocity because it's going down. Downward is negative, upward is positive. So it gets more and more and more negative, faster in the negative direction. So I was jumping forward to this. No, the acceleration doesn't change. It's always negative 10 meters per second squared everywhere here, which means 10 meters per second in that direction. That's why. So why doesn't it change? Because gravity doesn't change. Now back to the first one, does the ball's velocity change? Yes, the velocity changes because it's going up and it's accelerating downward, and then it's going downward and anytime you're accelerating, your velocity is changing. So I guess we could say, why? It's because there's acceleration from gravity. Acceleration means a change in velocity. Number 4, the difference between velocity and speed is that velocity includes direction. Speed is just how fast you're going. Like I've been saying, this could be a velocity of 40 meters per second, and this could be a velocity of negative 40 meters per second. The negative and the positive here, those tell us the direction. Positive means up, negative means down. The speed here and the speed here, they're the same. If this ball hit you and that ball hit you, it would feel the same, except it would hit you from a different direction. It would be moving 40 meters per second through the air. Number 5, to convert things from meters per second to miles per hour, you can just multiply them by 2. 25 meters per second times 2, and if I want my units to be right, I can say miles per hour per meter per second. And then the meters per second cancel out, and I get 50 miles per hour. Now that's not exactly right. If you want to get it more precise, you could multiply it by 2.24 or 2.239 to be even better, and you'll get something around 56 miles per hour. But this is good enough. Just double meters per second to estimate miles per hour. What does it mean? Somebody has a velocity of 4 meters per second. All this means is if this is the person and they're walking, oops, they've got a broken foot or something. Anyway, this person looks like they're going kind of fast, and they're going this way. After 0 seconds, they're there, and after 1 second, 1 second, they're here. See if I can make them look a little better. Nope, they're still having problems. So, and this distance right here, this distance that they have traveled is 4 meters. That's what that means. And after the next second, from 1 second to 2 seconds, they're going to go another 4 meters, assuming they keep this velocity. So all that means is they've gone 4 meters during 1 second. Number 7, this is a trickier one, but still it's easy to say once you get it. An acceleration of 4 meters per second squared. What does that mean? That means each second, 4 meters per second is added to your velocity. So up here we had 4 meters per second. This is how much is added every second. Now we've got 4 meters per second. This is how much is added every second. Up here with velocity, we're adding meters, we're adding position. With acceleration, we're adding velocity. And the fact that that says s squared gets everybody all confused. It might be easier just to write 4 meters per second, or say 4 meters per second. Separate those. So if I were to draw the people here, here's somebody that's just standing still, going 0 meters per second, and 1 second later, now they're going really fast. They're going 4 meters per second. And this is at 0 seconds, and this is at 1 second. If I continued this to do after 2 seconds, now they'd be going 8 meters per second after 2 seconds. And then after 3 seconds, they'd be going 12 meters per second. So you're just adding this on every second. Each second, that much is added. That's what acceleration means. Now if it's negative, that much is subtracted. Number 8, you could use your car's odometer. This is an odometer. The odometer is in the middle of the speedometer usually. It tells you how many miles the car has driven. There's really 2 parts to it. There's the trip set, which if you press a little button, that goes to 0, at least on the old cars. New cars, this is digital. And then you drive a little bit, and this tells you how many miles you've driven since you pressed the button. This tells you how many miles the car has gone since it was manufactured. So at any rate, this thing gives you the distance. That's what the odometer does. This part out here, that's the speedometer. That tells you speed. Doesn't tell you the direction the car is going. It's not a velocimeter. Doesn't tell you whether you're going north, south, up, or down. It just tells you how fast you're rolling along. So back to this, what formula would you use? Ooh, wish I had my formula sheet. Oh, I do. Got it from some other thing. So you says to find your average velocity. So you're looking for average velocity. I think on the test I actually labeled this average velocity, average V equals D over T, on the little sheet that I gave people. You wouldn't use final velocity. And the other bit of information you need for average velocity is you're going to need the time. This doesn't give you the time, it tells you the distance. And that's the formula. Average velocity is D over T. Which graph shows accelerated motion? This is the one. And you can pick it out because it's curved. If you have a distance versus time graph that's curved, it's accelerated motion. Now that's only true for distance versus time graphs. You got to know what kind of graph you're looking at. Now, why? It says in here, don't just tell me because of the shape. Don't just say because it's curved. I want to know what the curve tells us and how. So what it tells us is that in the beginning here, for these first 2 seconds, you can see the position is right about 0 the whole time. It doesn't change much. So whoever made this curve, whoever did this, walked in this fashion, or ran or drove a car, didn't go very far in those 2 seconds. Now if you pick the last 2 seconds from here to here, from 18 seconds to 20, they went from there to there. So they're at the, funny units. This is 60, 1, 2, 3, 4, 1, 2, 3, 4, 5 spaces in between. So each of these is 4. This is 64 meters all the way up to 80 meters. 80 minus 64 is 16. So they went 16 meters in the last 2 seconds. They hardly went any at all, less than 1 in the first 2 seconds. So that shows they're speeding up. And I just said, number 1 travels greater distances with each passing second. Number 10, when you plot points, I just drew the curve instead of, or maybe I plotted the points and drew the curve over it so you can't see it. I'm not going to go over how to plot points. I do want to say that there were some people who did this on the test. They plotted all these points, and then they did this. They did to draw a smooth curve that fits the data points. They just drew a line. Don't do that. It's not necessarily linear. If all of your points are in a nice little pattern like this, and they're forming this curvy line, then your trend is a curvy line. You just do that. If you have something that looks like this, where your points are all over the place, but kind of in a big fat line, then that's the kind of situation when you draw a linear fit. Points look like this, and they're all over the place, but not in a straight line, then you just do that. At any rate, what few people were doing wasn't the thing to do. Now on this, you can think about this a lot of different ways, but I guess I'm going to do it the quick way and then the good way. So wherever this is flat on a position versus time graph, that means somebody's not moving. Wherever it's curving up, that means they're getting faster, they're accelerating. Wherever it's straight but not flat, that means they're moving at a constant speed. Wherever it's curving downward, that means they're slowing down. And wherever it's flat again, that means they're not moving. So why? Flat means the position is staying the same the whole time. This is at 0 this whole time. This is somebody who's at 110 meters for this whole time segment, so they're not going anywhere. This is somebody who if I go over and up and over and up, what I'm doing here is I'm saying that during this 1 second interval right here, somebody is going from the 10 meter mark to the 20 meter mark. So they went 10 meters in that interval. And then if I go over another second and then up, I go from 20 to 30. So in this next second, they're going, it's a 1 second interval, they're going 10 meters. In the next 1 second interval, they're going